Hello physics students, this is chapter 7, part 3 video. So this next part is about tension, and we're going to revisit tension. Alright, so we have this illustration here of a safe, heavy safe hanging from this rope and making the rope be under tension. So if you can think about this tension as many molecular bonds that are stretched out, then you can think of the tension force pulling in both directions. In other words, there's a tension force from this rope pulling on the wall and pulling on the safe. And if you think of the action-reaction pairs, the safe is also pulling back against the rope, and the wall is also pulling back against the rope itself. So let's see here. We have this atomic level model in which tension is due to the stretching of spring-like molecular bonds within the rope. Stretched springs, they're like little springs, exert pulling forces, and the combined pulling force of billions of stretched molecular springs in the rope or string is what we call tension. An important aspect of tension is that it pulls equally in both directions. Example 7.5. This figure shows a student pulling horizontally with a 100 Newton force on a rope that is attached to a wall. In the other figure, two students in a tug-of-war pull on opposite ends of a rope, also with 100 newtons each. Is the tension in the second rope larger than, smaller than, or the same as that in the first rope? Let's think about it like this. All right, here is this dot. Let's let this dot represent the student. Let's let this dot represent the rope. Let's let this dot represent the wall. All right, the student is pulling on the rope. That's the force of the student on the rope. And then the rope is also pulling on the student. The rope on the student. And these two forces are an action-reaction pair. Meaning they have to be the same magnitude, opposite directions. But we know that in that situation, the rope is not moving. The rope is in static equilibrium. So in order for the rope not to move, there also has to be a force this way, which is going to be the force now of the wall on the rope, which is an action-reaction pair with this, the force of the rope on the wall. And these are action-reaction pairs. Again, for this to be, this rope to not move, the force of the student on the rope has to equal the force of the wall on the rope, which also has to equal then, this is because of Newton's first law, because F equals ma, and we're in static equilibrium, which means that A is 0, which means those two forces have to balance each other. Now we also know that the force of the wall on the rope equals the force of the rope on the wall because of Newton's third law. The law about action-reaction pairs being equal and opposite forces. And the same thing here, the force of the student on the rope equals the force of the rope on the student, also because of Newton's third law. So both of these, all these, we know this is 100, so this is 100, this is 100, this is 100, this is 100. So it's going to be the exact same situation as if this was a student pulling or another person pulling on that rope. It's going to be the same as the wall pulling on that rope. So even though kind of our intuition may think, well, gosh, if there's two people pulling on that rope, surely that's putting more tension in it than if just one person was pulling on the rope. But that's not the case because of Newton's laws, because of the action-reaction pair going on between the rope and the wall itself. Let me just say one more thing. There's also, you might be thinking, well, the student is also in static equilibrium, and that would be true also because of something we're not thinking about. We don't have to think about it, but it's there. What's balancing that is the force of friction between the student and the ground, balancing that out, static friction. And this would also be something here, the force of the ground on the wall. So that would also balance that, just for a thorough analysis there. Okay. Where are we? Back to the PowerPoint. If you want to pause it and look at explanation from the publisher. Feel free to do that and read through it. All right. Next, the massless string approximation. Often in problems, the mass of the string or rope is much less than the masses of the objects that it connects. In such cases, we can adopt the following massless string approximation. Okay, so we just assume that the string is massless in order to make this situation it's more simple for us to figure out. And that when we can do that when the mass of the connecting thing is kind of negligible or very, very, very small compared to the mass of the other objects themselves. When we have a massless string approximation, it means that the tension of object B on the string is the same as the tension of object A on the string, and that will always be the case. The tension of object B on the string and the tension of object A on the string are always going to equal each other when we assume that the string has no mass. Now, when we assume the string does have mass, which we may cover a little later, like if it's a chain or something that does have some significant mass to it, then we'll have to reanalyze this thing, but don't worry about that for now. Two blocks are connected by a massless string. As block B is pulled to the right, the force of tension of the string on object A and the force of the tension of the string on object B act as if they are an action-reaction pair. So the string on A is the opposite and equal magnitude of the string on B. So they act as if they're an action-reaction pair. They're not actually. The string on A would be the same. The action-reaction pair would be the A on the string, not the string on B. So they're not actually an action-reaction pair, but they act. It's going to be just as if it is that way because of what we just talked about. All a massless string does is transmit a force from A to B without changing the magnitude of that force. So it's like it's almost as if the tension of B on A is actually the same. It transmit the force of object B on object A, and the transmission, the tension of the string on B is really just as if it's the force of object A on B, because the string is just transmitting the forces between the two objects. For problems in this book, you can assume that any strings or ropes are massless unless it is explicitly stated otherwise. Quick check 7.5. Boxes A and B are being pulled to the right on a frictionless surface. Box A has a larger mass than box B. How do the two tension forces compare? Pause it and think about it. Okay, I'm going to address this two ways. One a simple way and one a more complicated but maybe more thorough way. Let's think about it like this. Okay. If this string is only pulling that, right? This T1 is only pulling box A, which has a bigger mass than box B. This T2, though, is not only pulling box B, it's also pulling box B and that other string and box A. It's kind of pulling this whole system, and that whole system has a bigger mass than just box A because it includes the mass of box A plus some other stuff. So tension 2 is actually having to do more than tension 1 is doing. So for that reason, T2 is going to be greater than T1. All right, now I'm going to think about it a different way. So it says that it's a frictionless surface. If it's a frictionless surface, the only... Let me go ahead over here to show you something. This may be slightly difficult to follow, but try to bear with it. Here's big M. All right. Here, let's call this string 1. I can't remember what. Let me just make sure I got my numbers right. Where's my PowerPoint? Yeah, that was tension 1, so we'll call that string 1. Then here is little m. So big M and little m, okay? Then here's, move it a little bit. Here's string 2. All right, now let's look at each one of these individually. We have a pulling force on string 2. We also have the force of the little m on string 2. We also have the force of string 2 on little m. And these are an action-reaction pair. We also have the force of string 1 on little m, along with the force of little m on string 1, and these are also an action-reaction pair. We also have the force of big M on string 1 and the force of string 1 on big M, which are also an action-reaction pair. Alright, now, because it said frictionless, the only force happening on big M is that, the only one that matters, you got gravity and normal force, but they cancel out, so they don't matter. The only force that matters here on big M is the tension force of the string, which I'm calling the force of string 1 on big M, which means that there has to be an acceleration to the right. That is a necessary truth. Acceleration will have to go that way. Okay, so knowing that, the whole system has to be that way. Every object's acceleration is going to point to the right because of that. So, knowing that then, we can say the force of string 1 on big M is equal to the force of big M on string 1. But the force of big M on string 1 must be less than the force of little m on string 1 because of the acceleration pointing to the right. This force right here has to be bigger than this force right here. Otherwise, the acceleration could not point to the right. And we also know reaction act. So this is Newton's third law. This is Newton's first law. This is an action-reaction pair with the force of S1 on little m because of Newton's third law. Newton's third law, action-reaction pairs. But then the force of S1 on little m must be less than the force of string 2 on little m because of Newton's first law again. Because the acceleration has to point to the right. And if the acceleration points to the right, this force of S2 on m, little m, has to be bigger than the force of string 1 on little m. Okay, and then this equals the force of little m on string 2, because again, Newton's third law. And then that has to be less than the pulling force on string 2, again because of Newton's first law, and the whole system accelerating to the right. So that's the thorough explanation to say, to compare all these forces. But it also answers the question that string 2, the string on the right, is a higher force or a higher tension than string 1. So I know that might have been somewhat confusing, but you know, that's what we got to do sometimes. All right. So the answer is the tension in string 2 is higher than the tension in string 1. Maybe the first explanation got you there quicker. Compare two tensions. Blocks A and B are connected by a massless string 2 and pulled across a frictionless table by a massless string 1. B has a larger mass than A. Is the tension in string 2 larger than, smaller than, or equal to the tension in string 1? This is a problem just like we just did in that quick check. It's the exact same thing. We already know the answer is going to be the tension in string 1 is bigger than the tension in string 2. So let's see what let's just read the explanation from the publisher. Massless spring approximation allows us to treat A and B as if they interact directly with each other. The blocks are accelerating because there's a force to the right and no friction. That's what I said earlier. B has a larger mass, so it may be tempting to conclude that string 2, which pulls B, has a greater tension than string 1, which pulls A. The flaw in this reasoning is that Newton's second law tells us only about the net forces. I think I was saying the wrong Newton law earlier. I was saying Newton's first law, but Newton's first law is inertia. I guess Newton's second law is F equals ma. So every time I said Newton's first law over here, and I think I said this earlier too wrong, but every time I said that, it should have been Newton's second law, which was what I meant. I just said the wrong number. But the F equals ma law is what I was trying to get at there. Sorry about that. The net force on B is larger than the net force on A. But the net force on A is not just the tension T1 in the forward direction. The tension in string 2 also pulls backward on A, which is what I was saying earlier. See, tension 2 only has to pull block B this way. But tension 2 is also pulling block A backwards, which makes tension 1 have to overcome that, which makes the tension 1 be actually bigger than tension 2, because tension 1 has to overcome tension 2 in order to pull block A to the right, and because it's the whole system that's moving to the right. You may be able to explain that to yourself better than I explained it to you. Here's the analysis. So tension 1 has to be bigger than tension 2, again, because of everything we said. And moving on. Alright, quick check 7.6. Boxes A and B are sliding to the right. They're sliding to the right on a frictionless surface. Hand H is slowing them down. So hand H is putting a force there on block B, but only because it's slowing them down as they move to the right. So in other words, the velocity is to the right, but the acceleration points to the left. Box A has a larger mass than B. Considering only the horizontal forces, what must be true about comparing all those forces? All right, pause it and think about it. Let's assess all these choices. The force of block B on the hand equals the force of the hand on block B. That has to be true because of action-reaction pairs. But this does not have to be true. The force of the hand on B is not necessarily equal to the force of A on B. And in fact, it can't be because we know that acceleration points to the left. If all these were equal, there would be no acceleration. Acceleration would be 0. Let's look at the second one. The force of block B on the hand is equal to the force of hand on block B. That's true. Which is greater than the force of block A on B, which is equal to the force of block B on A. I'm liking choice B right there because it means that the hand forces, which are going to point to the left, are going to be greater than the block A on block B forces, which are going to point to the right. I'm liking that, but let's keep looking. The B on the hand on B is less than. That would not be true, otherwise it would be accelerated to the right. So I'm going to skip C and look at D. The force of the hand on block B is equal to the force of the hand on block A. That's already wrong because the hand is not even touching block A. So it's got to be choice B. And that's right. All right, let's stop right there for part 3 before we get into pulleys.